In this video and the next, we will be talking about section 2.3 and section 2.4 inverses together. At the end of the last video, we say that when A reduced row echelon form R, we can find some elementary matrices such that the product of the elementary matrices and A is the Rth matrix. So, and lumping these elementary matrices together, we have a P matrix, and this P matrix is invertible. It's a product of elementary matrices. Now we can make the following conclusion. This is a theorem 2.3. A is an n by n matrix. It has a reduced row echelon form R. Then we can always find an invertible n by n matrix P such that PA is the R matrix. And this P matrix, as we have found out earlier, is actually a product of elementary matrices. Now we have some questions here. Suppose A n by n and the reduced row echelon form is R, and suppose that R is the identity matrix. Would A be invertible? Let's try to use the theorem that we have just talked about to solve this. Pause and think about it. Ready? Theorem 2.3 said we can always find P such that this is true, invertible P so that this is true, right? So we can find an invertible P such that PA is the identity matrix. P is invertible, so there's P inverse. Let's apply P inverse on both sides. And what do we get? The P inverse P cancel off, and we are left with A equal to P inverse. P is invertible, so P inverse is also invertible. So yes, indeed, if reduced row echelon form is the identity matrix, A is invertible. Continue on the same question. We already know that A is invertible, right? Is A a product of elementary matrices? Pause and think. Ready? We already know that A is equal to P inverse. So the question is whether P inverse is a product of elementary matrices, right? And we also know P itself is a product of elementary matrices. We can write P like so. And A is P inverse. The inverse of a product will now become E1 inverse, E2 inverse, EK inverse. And we already know that the inverse of an elementary matrix is also an elementary matrix. So E1 an elementary matrix, E1 inverse an elementary matrix, E2 inverse an elementary matrix. Each one is an elementary matrix. So A is also a product of elementary matrices. So yes. Now let's combine two results together. This result here told us that if R is the identity matrix, A is invertible. Earlier we had the conclusion that when if A is invertible, then the reduced row echelon form is the identity matrix. So A invertible, reduced row echelon form the identity matrix. And just now we just saw that whenever the reduced row echelon form is the identity matrix, it implies that A is invertible. So this is an if and only if statement. A is invertible if and only if the reduced row echelon form is the identity matrix. So this ties nicely the invertibility of A matrix to its reduced row echelon form. On the other hand, we have also seen that when R is the identity matrix, then A is a product of elementary matrices, which imply that A is invertible. And using this result, we know this also implies R is the identity matrix. So again, all these are equivalent. R is the identity matrix, A is a product of elementary matrices, A inverse exists, A is invertible. All these three statements are equivalent. Theorem 2.6 gives a summary of equivalent statements about invertible matrices. First of all, A is invertible if and only if the reduced row echelon form R is the identity matrix. And this is the same as saying that the rank of A is equal to n. is equal to the number of rows. For the case that A is m by n and rank A is the same as the number of rows, then actually these three are equivalent. Rank A equal to the number of rows. Span of a column of A is equal to Rn. Well, earlier when we talked about this, it was Rm, but now m is equal to n. And A x equal to b consistent for all b in Rm, but now it's Rn. Now that rank A is equal to n, nullity of A will be equal to 0. It's equal if and only if nullity of A is 0. From what we have learned earlier, this is if and only if. This is true if and only if the columns of A are linearly independent, and if and only if the solution of the homogeneous equation is unique. So statement A to H, all these are equivalent statements. And just note, we have learned one more thing. The reduced row echelon form is the identity matrix if and only if A is a product of elementary matrices. Well, so A is invertible if and only if A is a product of elementary matrices. So now we are only left with I and J. What does I say? There exists an m by n B such that BA is the identity matrix. There exists a B such that BA is the identity matrix and AB is the identity matrix, then B is the inverse of A, right? But now this statement has only half of it. There exists a B such that BA is the identity matrix. So it turns out we don't need AB is the identity matrix to make A invertible. We only need M by M B matrix such that BA is the identity matrix. And similarly, if we can find an C by C matrix such that AC is the identity matrix, then it is sufficient. It's already enough for A to be invertible, because this is going to be an equivalent statement for invertibility of A as well. If A is invertible, then of course there exists B such that BA is the identity matrix, so A imply I. And similarly, A imply J as well. So we already know that A imply I and A imply J. We only need to show that the converses are true. I imply A and J imply A. To show that I implies A, well, it's enough to show that I imply any of the other equivalent statements we have already established. For example, if we can show I imply H, then that's good enough too. What is H? Solution of the homogeneous equations unique. According to I, we have an M by M B such that BA is the identity matrix. Now let's consider the homogeneous equation. Because BA is the identity, so let's multiply B on both sides. Then what do we get here? We get BA the identity, so we get X on the left hand side and 0 on the right hand side. So if we have a B matrix such that BA is the identity, then it implies directly that the solution of the homogeneous equation is the 0 vector. So there we have it. I implies the solution of the homogeneous equation unique. Now we want to show that J imply A. We can show J imply any of the equivalent statements. So for example, we can show that J imply E. E statement says the equation AX equal to B has a solution for all B. J says that there exists a C matrix such that AC is the identity matrix. Let's form the matrix vector product on both sides. We add a B matrix on both sides. Then we get ACB equal to IMB, and IMB will simply be B matrix, right? Now we get the conclusion that A and the CB is equal to B, and this is for arbitrary B vector in Rn. What does this mean? Let's call this vector X. On the left-hand side, we have the matrix vector product equal to B vector, and this is true for all B in Rn. So the conclusion that we get from here is Ax equal to B has a solution for all B in Rn. What is the solution? The solution is simply CB here. So there we go. J does imply E, and E is the same as saying that A is invertible. So again, J is an equivalent statement.